Okay. Now, the next section in this chapter is determining the formula of compounds. Here we can distinguish between two types of formulas. The first type is called molecular formula, and the second one is called empirical formula. The difference between them is that in molecular formula, you will find the actual subscripts without simplification. While in empirical formula, here the subscripts should be simplified to the smallest whole number, What we mean by that? Here we have some examples. For example, benzene, it has a formula of C6H6, and this is the molecular formula of benzene because it's not simplified. After simplification, I mean by simplification is finding the common factor between the two subscripts. Here 6 and 6, so we can simplify them to 1 and 1. So the common factor here is 6. This is the integer that is used to simplify C6H6 into CH. So this is the empirical formula CH, while C6H6 is the molecular formula. The same idea can be applied in hydrogen peroxide, H2O2. This is the molecular formula without simplification. Now, if you simplify it, it will be HO. This is the empirical formula. And here the integer or the common factor is 2. For N2O, as you can see, N2O cannot be simplified anymore, which means the molecular formula and the empirical formula are the same. And the integer is 1. In general, to determine n, where n is the common factor, 6, 2, or 1, you can apply this formula. N equals the molar mass of molecular formula over the molar mass of empirical formula. So let's try it here for the first example. N, we know that in advance it's 6, but let's try to find it by applying this law. Molar mass of molecular formula, so it will be molar mass of C6H6. C6H6 is 78 over molar mass of CH, which is 13. Now when you divide 78 over 13, it will be 6. So this is how to determine the value of the common factor. Now let's solve this example together. In this exercise, we have adipic acid, where adipic acid is a name of an organic compound. The name is not important. The composition of adipic acid is 49.3% carbon, 6.9% hydrogen, and 43.8% oxygen by mass. The molar mass of adipic acid is given, it's 143. And here the question asking you to determine the empirical formula and to determine the molecular formula of adipic acid. Here the answers are given, but how can we get these answers? Now let's think about it. Adipic acid consists of carbon, hydrogen, and oxygen. And the question asks us to determine the empirical and molecular formula. As you know, to determine any formula, you should write the atoms that exist in your compound or molecule. In this case, the type of atoms are carbon, hydrogen, and oxygen. But this is not enough. To write correct formula, then you should write the subscript of each atom. So let's say the subscript of carbon is X, the subscript of hydrogen is Y, and the subscript of oxygen is Z. They are not given in the question, which means if we are able to determine the values of X, Y, and Z using whole numbers, then we can easily get the answer. Now from the question, the percentage of each one of these three elements is given. The percentage of carbon is 49.3%. This is carbon. And the percentage of hydrogen is 6.9%, all by mass, while the percentage of oxygen is 43.8% by mass. Now, as we discussed earlier, these percentages are independent on the mass of any sample, which means if I have 1 gram of adipic acid or 100 grams of adipic acid or 1000 or 1 million gram, these percentages are constant according to the law of definitive proportion that we have explained in chapter 2. What does it mean? It means that any mass of adipic acid will contain the same percentages of these three elements. So for simplicity and to simplify the solution, and because the mass is not important, let's assume that we have any mass of adipic acid. Here you can make any assumption. You can assume you have any mass. Let's say you have 100 grams. Assume you have 100 grams of adipic acid. Again, it's not necessary to consider this assumption. You can assume you have any other mass you want. All will give you the same answer, adipic acid. So the percentage of each element is given. Carbon, the percentage of carbon by mass is 49.3%, which means we can determine the mass of carbon in adipic acid. So now we can determine the mass of carbon in this sample. The mass of carbon equals the percentage of carbon, which is 49.3%, 49.3 over 100. This is 100 from the percent sign, times 100 grams, which is the mass that we assumed. So 100 with 100 will cancel one another. So the mass is 49.3 grams. Now X here, this is the subscript of carbon. And we explain that these subscripts, they have two meanings. The first meaning is the number of atoms. So when I say, let's say here, this is just an illustration. It's not related to the exercise. When I say I have H2O, then it means that you have two hydrogen atoms to one oxygen atom. So this is the atom ratio, And at the same time, we can say we have 2 moles of hydrogen to 1 mole of oxygen. Both are the same. These two ratios are the same. The particle ratio, which is the atomic ratio, or the mole ratio are the same. Do you know why? What's the relation between number of atoms, which is number of particles, and number of moles? Do you remember the law? Yes. Number of moles equals number of atoms or particles in general over Avogadro. So as Avogadro is a constant, it means that this ratio will remain the same. Because to convert atom to mole or mole to atom, we need to multiply or divide by Avogadro. And here we should do the same. You should multiply or divide by Avogadro. As you are multiplying or dividing using the same constant, which is Avogadro number, then the ratio will be the same. What does it mean in summary? In summary, we can say that the subscripts in any molecule represent two meanings. The first meaning is the ratio between atoms, the atom ratio, the particle ratio, or the mole ratio. Both are correct. But I prefer to deal with moles because always number of moles is smaller than number of particles. If you are dealing with particles, then you will deal with huge numbers with powers 22, 23, 24. So for simplicity, we prefer to deal with moles. So because these subscripts represent mole, so we can understand that X is the number of moles of carbon, Y number of moles of hydrogen, and Z number of moles of oxygen in adipic acid, the mole ratio between them. Now let's apply this idea to continue our solution. Because X is number of moles of carbon, the mole ratio of carbon, and because moles, as we have explained, equals mass over molar mass, so we can determine the value of X. X equals the mass of carbon, which is 43.9, over the molar mass of carbon, which is 12 from periodic table, and the answer is 4.108. Apply the same method to determine the value of Y. Y is the moles of hydrogen. Let's determine the mass of hydrogen first. Mass of hydrogen is the percentage of hydrogen, 6.9 over 100 times 100, so it's 6.9, which means Y is moles of hydrogen, 6.9 over molar mass of hydrogen 1, so it's 6.9. Here is X, here is Y. The last one is Z, which is moles of oxygen. Now the mass of oxygen equals the percentage of oxygen, which is 43.8. 43.8 times 100 grams, which means Z moles of oxygen is the mass. So here 43.8 grams over 16, the molar mass of oxygen. And the answer is 2.738. 2.738. Now we got the values of X, Y, and Z. Let's write them now. Here is carbon. The subscript of carbon is 4.108, hydrogen 6.9, oxygen 2.738. Now these ratios, as I said, they represent the mole ratios between carbon, hydrogen, and oxygen. The ratio is 100% correct. But what's wrong with this formula? The wrong is that, or the incorrect information is that these subscripts, they are fractions. And as you know, to write a correct formula, we should write the subscripts in terms of whole numbers. So what shall we do in this case? Simply, you can divide over the smallest number among these three numbers. The smallest number is 2.73. So divide this over 2.738, 2.738, sorry. And the last one over 2.738. 2.738, and this is over 2.738. The results is that here, when you divide them, this will be 4.1, 4.108 over 2.738, it's 1.5. 6.9 over 2.73, this is 2.5, and for oxygen it's 1. Here is 1. Again, we did not get whole numbers, but as you can observe, the fractions became regular fractions. 1.5 and 2.5, they are regular fractions. Sometimes, in many cases, after this step, after the division, you can end with whole number and you can get the answer. But in other examples or in other cases like this, we will not get the answer directly, so we need to carry out a further step. This step is what? Just ask yourself, what is the integer that we need, the smallest integer, that can convert these subscripts into whole numbers. Which integer which integer can we apply to convert these subscripts into whole number? The answer is 2. If you multiply by 2, then C here, carbon, will be 3, so it will be C3, and hydrogen will be 5, while oxygen is 2. C3H5O2. Because C3H5O2 is the simplest formula, then it represents the empirical formula of adipic acid. This is the empirical formula. This is how to solve such type of questions. Now go back to the example here, to the exercise. The exercise, don't forget, we have two parts. The first part is the empirical formula, which is done. Now let's proceed to the second part, which is the molecular formula. How can we determine the molecular formula of adipic acid? As we said previously here, to convert molecular to empirical or empirical to molecular formula, we need to determine the value of the common factor. To determine the value of the common factor, we can apply this formula. N equals the molar mass of molecular over molar mass of empirical formula. So let's try to apply it here. N equals molar mass of molecular formula. It's given in the question. Here is the question. The question gave us the molecular formula. Can you see here the molar mass of the molecular formula? It's 146. So this is 146 over molar mass of empirical formula. The empirical formula is C3H5O2. We already determined it in part number 1. So go to periodic table and determine the molar mass of this empirical formula. 3 times 12 plus 5 times 1 plus 2 times 16. The answer is 73. So the value of N is 2. What does it mean? It means to write the molecular formula, we need to multiply all subscripts in empirical formula by 2. Multiply all subscripts by 2. When you multiply them, the answer will be C6. Here multiply everything by 2. And the final answer is C6, sorry, C6, H10O4. This is the molecular formula of adipic acid. Now the next topic in this chapter is balancing chemical equation. How to balance chemical equations. As you know, chemical equations are the equations that represent chemical reactions. And in all chemical equations, as you can see here, we have this reaction between 1A. This is just a representative equation. 1A plus 2B produce 1C and 3D. These numbers 1, 2, 1, and 3, these are called coefficients. And they represent the mole ratio between the reactants or the products, or between the reactants with each other and the products with each other. So it's a mole ratio or a particle ratio, a molecule ratio. It's similar to subscripts. Similar to subscripts. So don't forget it. Coefficients represent the mole ratio. When I say A plus 2B, it means 1 mole of A to 2 moles of B. 1C and 3D, 1 mole of C to 3 moles of D. We have an arrow between them. In the left side, you can find the reactants, and in the right side, you can find here the products. Also, you can find in brackets here, sometimes you can find these abbreviations. S stands for solid, L stands for liquid, G gas, and AQ is aqueous. Well, aqueous means water, any material dissolved in water. And this will be, inshallah, the title of chapter number 4, in which we'll talk about the aqueous solutions. Now, let me give you some examples to balance the chemical equations. Balance the following chemical reactions or chemical equations. The first reaction is the reaction between methane, CH4, and oxygen. The products are carbon dioxide and water. To balance the equation, we prefer to start with molecules or compounds before starting with elements. This will simplify the solution. Oxygen is element, CH4 is molecule, so start with molecule before element. This is the first hint. The second hint, you can change the coefficients as you want. Change them as you want to balance the equation, but never ever touch the subscripts. It's totally forbidden and not allowed to change the subscripts. This is very important note. Balancing chemical equation means making the number of moles or the number of atoms in the left side equals the number of the same atoms in the right side. So you should count how many carbon atoms you have in left side and make it equal to number of carbon atoms in the right side or the product side. How can we make them equal? By changing the coefficients. Now let's try it. How many carbon atoms we have in the right side? We have only one carbon atom. And here we have one carbon atom in the product side, which means we don't have any problem with respect to carbon. Now move to hydrogen. Here we have 4 hydrogens, while in water we have 2 hydrogens. So to make them equal, we need to multiply water by 2. When you multiply, change the coefficient of water, then you will get 4 hydrogens in the left and 4 hydrogens in the right. So here we balanced the hydrogen atoms. The last atom is oxygen. Here we have 2 oxygen atoms. Now count how many oxygens you have in the product side. You have 2 from carbon dioxide and 2 from water. So the total is 4. While here we have 2. To make them 4, you should multiply O2 by 4. So multiply it by 2. Now they are 4. So this equation is balanced now. Another example. Let's say you have a reaction between C6, H6, and O2. The products again, the products of this reaction is carbon dioxide, CO2, and water. Apply the same method. Here we have 6 carbons. Here we have 1 carbon. So I need to multiply carbon to change its coefficient to 6. We have 6 hydrogens here, 2 hydrogens in water, so multiply this by 3. Here we have 2 oxygens, while here how many we have? 6 times 2, we have 12 oxygens from carbon dioxide and 3 oxygens from water. The total is 15. 12 plus 3 is 15, while here we have 2. So to make them equal, we need to multiply oxygen by 15 over 2. Here the coefficients can be written in terms of a fraction. We don't have a problem at all if you write the coefficients in terms of a fraction. Not like the subscripts. The subscript, they should be always written using whole numbers, but in coefficients, no, we don't have a problem at all. If you don't like fractions, how can we get rid of this fraction? Yes, you can multiply everything by 2. So if you multiply it by 2, you will get 2C6H6 plus 15 O2, and here 12 CO2 and 6H2O. Both are, you can either use or you can apply any one of them. This is how to balance chemical equations. You can solve as much questions as you can from the textbook. You have several examples. We don't have time to solve more examples with respect to this point. Now, let's solve this exercise together. Which of the following correctly balances the chemical equation given below? There may be more than one correct balanced equation. If a balanced equation is incorrect, explain why it's incorrect. The equation is CaO plus C The products are CaCO2, sorry, plus CO2. Now to balance the equation, we can use the traditional method. Here we have one calcium, here we have one calcium, so it's okay. Here we have one oxygen, here we have two oxygens, so I need to multiply this by 2. When we multiply CaO by 2, then we got two calciums, which means we should modify the coefficient here of CaC2 to be 2. The last atom is carbon. Here we have one carbon, while in the product side we have 2 times 2, 4 from CaCO2, and we have 1 from carbon dioxide, so the total is 5. So I need to multiply this by 5. The coefficient here should be 5, the coefficient of carbon. Now, if we check the three answers, our answer is similar to answer 2, so this is correct. Now, the question informed us that you may have more than one correct choice, which means we should check them all. Let's check the first choice. Here we have one calcium, and here one calcium. Here we have two oxygens, and here we have two oxygens. It's okay. Here we have 3 carbons, and here we have 2 plus 1 is 3 carbons. So this equation is balanced. What do you think? Is it correct or incorrect solution to our equation to this compared to this? Yes, you are right. This is wrong choice. Why it's wrong choice? Because to balance this equation, what did he do? He changed the subscript. Can you see here the subscript of CaO is 2, CaCaO2, while in the original equation it's CaO. Is it allowed to change the subscripts? No, it's not allowed. This is why this choice is wrong. Let's now check the third option. What's the relation between the second option and the third option? Look. Yes, the relation between them in the second choice here, the subscripts in the coefficients in the subscripts are multiplied by half. We multiplied everything by half, which is allowed. 2 times half is 1. 5 times half is 2.5. 2 times half is 1. And 1 times half is half. So this is also correct. What about the last choice? The last choice is also correct because the relation between the second, which is our choice, and the last one, every or all coefficients in choice number 2 are multiplied by 2. 2 times 2 is 4. 5 times 2 is 10. 2 times 2 is 4. 1 times 2 is 2. This is why the fourth choice is also correct. So all of them are correct except the first choice. What do coefficients represent in a balanced chemical equation? For example, here, if you have the reaction between 2 hydrogen and 1 oxygen, and the product is 2H2O. This is a balanced chemical equation. Now the question is, what do these coefficients 2, 1, and 2 represent? As we said, they represent the molecule ratio. We can say for 2 molecules of hydrogen, you should have 1 molecule of oxygen, which will produce 2 molecules of water. So here, this is the particle ratio, because number of molecules is number of particles. Particles ratio between reactants and the products. And also, the particle ratio is equal to the mole ratio. Mole ratio. So we can say that 2 moles of hydrogen to 1 mole of oxygen to 2 moles of water. Both are the same. Why they are the same? Because to convert particles to moles or moles to particles, you need to divide or multiply by Avogadro. And because Avogadro is constant, the ratio will remain the same. Which is easier again to deal with moles or to deal with particles? Yes, we prefer to deal with moles. Both will give you the same answer, the same everything, but I prefer to deal with moles. Which of the following are true concerning balanced chemical equation? There may be more than one true statement. The number of molecules is conserved. What do you think this statement? Is it correct or incorrect? To answer the question, you should understand it. What we mean by number of molecules is conserved. When we say conservation, conservation of mass, conservation of energy, it means that the total number should be the same initially and finally. So when we study conservation of mass, the total mass initially and finally in any process should be the same. When we say conservation of energy, total energy initially and finally should be the same. Conservation of number of molecules, it means the initial number of molecules should equal the final number of molecules. Is it correct or incorrect statement? Let's apply this statement to the previous examples here. Here, for example, here we have this balanced chemical equation. Can you see it? How many molecules you have in the left side? This is the initial state. The reactants always are the initial state and the products is the final state. So initially we started with one molecule of CH4 and two molecules of oxygen. The total is 3. Here we have 3 molecules. How many molecules did we end with? We ended with one molecule of carbon dioxide and two molecules of water. So again here we got 3 molecules. So in this equation, number of molecules is conserved. But is it the case all time? Is this the case in all examples? Let's check this equation. How many molecules you have in the reactant side? You have 2 here and 15 from oxygen, so the total is 17. How many molecules you have in the product side? You have 12 carbon dioxide and 6 water, so the total is 18. Is it conserved? No, it's not conserved. So what's the final conclusion now? The final conclusion is that it's not necessarily that the number of molecules is conserved in all balanced chemical equations. So this statement is incorrect. The coefficient tell you how much grams of each substance you have. Is it correct or incorrect? What we said about coefficients, what do they represent? Yes, they represent the particle ratio, the ratio between number of molecules, or the mole ratio, but they don't represent the grams ratio. So here when we say we have 2H2 plus 1 O2 to produce 2H2O, we cannot say we have 2 grams of hydrogen to 1 gram of oxygen to 2 grams of water. This is incorrect. These coefficients are moles or particles. So this is why the second statement is wrong. The third statement, atoms are neither created nor destroyed. Yes, I think all agree with me. This statement is correct. If you start with carbon, hydrogen, oxygen, you should end with carbon, hydrogen, and oxygen. You will never ever end with gold. If we end with gold, you will, all chemists are billionaires, but this is not the truth. This is not the truth. The coefficients indicate the mass ratios of the substances. It's similar to the second statement. Again, this is wrong. The sum of coefficients on the reactant side equal the sum of coefficients on the product side. What do you think? It's similar to which statement? Yes, it's similar to the first statement. So this is again a wrong statement. The only correct statement is the third one. Now let's proceed to the stoichiometric calculations. Stoichiometric calculation, this is the core and the key topic in the chapter. Don't forget, stoichiometric calculations are the calculations that are related to the quantities or the amounts of reactants or products in any balanced chemical equation. If we have this balanced chemical equation, 2A plus 1A plus 2B produce, let's say, 3C, any question asks you to determine the amount of A or B or C, it means that this question is stoichiometric problem, and you should apply the stoichiometric principle. And the amount, when we say amount, don't forget again, amount has 3 meanings. We explain it in at the beginning of the chapter. حكينا إنه الأماونts, it may be number of particles or mass or moles. So that if the question asks you to determine particles or mass or moles of A, B, or C, then you should apply the stoichiometric principle. What's the stoichiometric principle? It's listed here. Stoichiometric principle states that are applied to determine the amount of particles, moles, or mass of any substance in balanced chemical equation. The principle is here. The principle, write mole ratio using the coefficients between the given substance, the substance that I have any information about it, about its amount, and the wanted substance, the substance in the chemical equation that the question asks you to determine its amount. So simply, in all stoichiometric problem, when you read the question, you will find that one of the materials, at least one, in the reactant or the product side is given. Given means we need, or we have an available information about its amount. The same question will ask you to determine the amount of another material, another reactant or another product. So here you should identify the given substance and the wanted substance. After that, write the mole ratio between them using the coefficients in the balanced chemical equation. Let's take an example. Consider the following reaction between P4 plus 5O2. The product is 2P2O5. The equation is balanced. If 6.25 grams of phosphorus is burned, so here when we read this statement, we conclude that phosphorus, which is P4, here we have the mass of phosphorus. Let's write it here again, P4 plus 5O2. The product is 2P2O5. The question gave me the mass of phosphorus. It's 6.25 grams. So for me, phosphorus is given in this case, in this example. What mass of oxygen does it combine with? The question asked me to determine the mass of oxygen. So oxygen here is wanted. This is the first step and the most important step. You should identify the given and the wanted material. After that, write mole ratio between them. This is the stoichiometric principle. Write mole ratio between given and wanted using the coefficient. The coefficient is P4 is 1, while the coefficient of O2 is 5. So here the ratio between them is 1 to 5. Write it here. 1 what? 1 gram or 1 mole? What do you think? Yes, it's 1 mole because we said coefficients are moles. So this is 1 mole of P4 to 5 moles of oxygen. Again here, as we mentioned previously, in any ratio, you should apply the consistency. What we mean by consistency? Consistency means each side should have the same unit and should be related to the same material. Here in the left side, we have mole P4. So any number written here should be moles of P4. In the right side, we have moles of O2. Any number here should be moles of O2. Now the question didn't give me the moles of P4. We have what? We have the mass of P4. Can we substitute mass under moles directly? No, we cannot, because here the unit is a gram, while here the unit is mole. So what shall we do? Yes, you should convert mass to moles. How to convert mass to moles? We already studied two formulas to convert or to determine moles. One of them, moles equals mass over molar mass. So here to determine moles of P4, you should divide the mass, which is 6.25, over molar mass of P4. I think it's 124. Yes, it's 124. The answer is 0.05 mole. 0.05 mole. Now we can substitute this value here because the unit is mole and in the ratio we have mole. So here is 0.05 mole of P4 and here we have X. Can we determine X? Yes, easily we can. By what? By cross multiplication. So X equals this item multiplied by this item over 1. So it's 0.05 times 5 is 0.25 over 1. It will remain the same, 0.25. X under O2. So the unit is mole because here we have mole. and under O2 means this is moles of O2. Did we solve the question? No, not yet. The question asked me to determine mass of oxygen, not moles of oxygen. So the last step is to determine the mass of oxygen. We know that moles, which is 0.25 mole of O2, equals mass of oxygen over molar mass, which is 32. When you multiply them, the answer will be 8 grams. This is how to solve the stoichiometric properties. Another example is here. Methane reacts with oxygen in the air to produce carbon dioxide and water. Ammonia reacts with oxygen in the air to produce nitrogen monoxide and water. Write balanced chemical equation for each of these reactions. Let's start with the first reaction. Here the reactants are methane and oxygen. So these are the reactants. CH4 plus O2. To produce carbon dioxide, this is the first product, and water, this is the second product. To balance the equation, we can easily balance it. Here we have one carbon, here we have one carbon, here 4, so you should multiply this by 2 and this by 2. The second equation, ammonia reacts with oxygen, so the reactants are ammonia. Ammonia and oxygen to produce nitrogen monoxide, NO, and water, H2O. To balance the equation, here we have 1, here we have 1, here we have 3 hydrogens, 2 hydrogens, so multiply this by 3 and multiply this by 2, multiply this by 2, and oxygens should be multiplied by 5 over 2. 5 over 2. So this is the first part of this question. The second part here, part 2, the same question, but part 2. What mass of ammonia? So the question asked me to determine ammonia. Let's write the equations again here. The first equation was CH4 plus 2O2, CO2, and 2H2O. The second equation is ammonia. It was 2NH3 plus 5 over 2 O2. The products are NO, 2NO, and 3 H2O. What mass of ammonia? Here is ammonia. So the question asked me to determine the mass of ammonia. So ammonia is wanted material. Would produce the same amount of water as 1 gram of methane reacting with excess oxygen. 1 gram of methane, 1 gram of CH4. So methane is given here. We have, from the question, we have the mass of methane. This is given. Stoichiometry principle told us write mole ratio between given and wanted. But here we have a problem. The given material is methane. It's in the first equation, while the wanted material, ammonia, in the second equation. Can we write mole ratio between them? No, we cannot, because they are in different equations. So this is why we cannot solve this question directly by writing the ratio between methane and ammonia. They are in separate equations, and I cannot apply the stoichiometric principle between them directly. So we have to read the question. The question must give us a common factor, a common information between the two equations. Read again. What mass of ammonia would you produce? Here it's written in the blue, the same amount of water. So according to this assumption, the amount of water in the first equation equal the amount of water in the second equation. These have same amounts according to the question. Now, can we determine the amount of water in the first equation? Yes, we can. So here, water is wanted in the first equation, and we can determine its amount because CH4 is given, and we can write ratio between CH4 and water, it's 1 to 2. So let's start with the first step now. The first step again is to determine the amount of water in the first equation. Then we can say that this amount equals the amount of water in the second equation. So water will be given after doing this step. Water will be given. And the last step is determining the mass of ammonia. So here, 1 mole of methane, which is given, we produce 2 moles of water from the first equation. We don't have moles of methane. The question gave me mass of methane. How to convert mass to moles? Yes, divide over molar mass. The molar mass of methane is 16, and here is x. By cross multiplication, x equals 2 over 16, 1 over 8, it's 0.125 mole of H2O, which equals what according to the question? It equals here, it's the same amount of water in the second equation. So it equals the amount of H2O in the second equation. So here we have 0.125 moles of water. Now, water in the second equation, it became available. The amount of water is available. So water is given here and ammonia is wanted. The ratio between ammonia and water is 2 to 3. Write it now here. 2 moles of ammonia produce 3 moles of water. The amount of water is 0.125 because it equal the amount of water in the first equation, here mole and here is x. By cross multiplication, x equals 2 times 0.125 is 0.25. 0.25 over 3 equals 0.083 mole of ammonia. This is not the final answer. The final answer is the mass because the question asked me to determine what mass of ammonia. We need to determine mass, and here 0.083 mole equals mass of ammonia over molar mass. So the mass of ammonia is 0.083 times 17. It's 1.42 grams. This is the final answer. It's 1.41 or 42 grams. The next topic in this chapter is limiting reactant. Limiting reactant, this is very important topic and very important concept. You should know the meaning of limiting reactant. To clarify the idea of limiting reactant, let me give you an example. Now, if you want to make a burger sandwich, and you found that you have only one piece of beef and 10 or 6, let's say, pieces of bread. Let's say this is a reaction. Beef will react with the bread to produce the burger sandwich. For each burger sandwich, you need 2 pieces of bread and 1 piece of beef. Now, my question is, which limits the amount of a product, which is the burger sandwich here? Which limits this amount? Is it beef or bread? Yes, the answer is beef. So why beef limits the amount of the product? Because it's consumed completely. Here in this process, we consumed the entire amount of beef and 2 pieces of bread. while 4 pieces will remain without reaction, or we will not touch them. These are called excess reactant. So in a similar way, if you have a reaction between two materials, A and B, to produce C, if A consumed completely in the reaction, used up, consumed completely, which means the entire amount of A reacted, then A will be the limiting reactant because it limits the amount of a product. And B is called excess reactant. A is the beef and B is the bread. I hope the idea is clear, but to illustrate it more, let's take this example. Here we have a reaction between nitrogen and hydrogen to produce ammonia. Nitrogen is represented by these two blue balls. Hydrogen is represented by these two white balls. Ammonia is represented by this blue ball with 3 white balls. Here is the reaction vessel between nitrogen and hydrogen. After the reaction is over, we ended with this scene. Now look, do we have any excess hydrogen or nitrogen that didn't react? We don't have. If you look and you observe, you will find that no hydrogen or nitrogen remained at the end of the reaction. What does it mean? It means both of them reacted completely. Both of them consumed completely. So here both of them are limiting reactant. Limiting reactant again is the reactant that consumed completely, and as a result, it will limit the amount of the product. It will indicate the amount of the product. These are the two key points about the limiting reactant. The complete consumption, الاستهلاك الكامل, and because it's consumed completely, it will indicate the amount of the product. The same reaction is here. Same everything. This is hydrogen, nitrogen, and ammonia. But what can you observe here at the end of reaction? What the difference between this scene here, and this scene here? What the difference between them? Yes, the difference is the presence of these two blue balls, which are nitrogen. So nitrogen here remained at the end of the reaction, some of nitrogen remained at the end of reaction as unreacted material, as a raw material. So nitrogen here is excess. Nitrogen is excess. Because nitrogen excess, hydrogen is the limiting reactant. If one of reactants is excess, then the other is limiting reactant. As you can see here, we don't have any traces of hydrogen at the end of the reaction. The entire amount of hydrogen reacted. So here we can conclude that hydrogen is the limiting reactant. In these examples, it's very easy to identify the limiting and the excess reactant. But in some problems, you cannot do this directly. Look at this exercise. In one process, 124 grams of aluminum reacted with 601 grams of iron 3 oxide according to this equation. Calculate the mass of Al2O3 formed. The solution is here provided here, but let us solve it together from the scratch. 2Al plus Fe2O3. The products are Al2O3 and 2Fe. Read the question again. In one process, 124 grams of aluminum. So the aluminum is given 124 grams. Reacted with 601 grams of iron 3 oxide. 601 grams. So this is given. And this is also given. Calculate the mass of Al2O3. Here we need the mass of Al2O3. This is wanted. This is wanted. Stoichiometry principle states that write mole ratio between the given material and the wanted material. But here, as you can see, two materials are given, two reactants are given. If I select aluminum in the ratio will be 2 moles of aluminum to 1 mole of aluminum oxide, then I'll get an answer. If I select Fe2O3, the ratio is 1 to 1, so I will get another answer. Which answer is correct? One of them is correct. Which one is correct? Do you know? Yes. The correct answer is the answer that is given if I write ratio between the limiting reactant and the product. This is an illustration of the idea of the limiting reactant. Here we cannot tell which one of them is limiting reactant, which one is beef and which one is bread. We cannot tell directly. So how can we determine the limiting reactant? The answer is by applying this methodology, apply this procedure. First step, determine the moles of each reactant you have. So here, determine the moles of Al. Its mass over molar mass, 124, over molar mass of aluminum is 27. And the answer is 4.59 moles. Sorry. This is 4.59 mole of aluminum. Now determine the moles of Fe2O3 you have. By the way, this procedure is applicable for all limiting reactant problems. Just apply the same steps. You will end with correct answer. Mass over molar mass, 601, over molar mass of iron 3 oxide. Iron 3 oxide is, I think it's 160. So the answer is 3.76 mole. Next step, write mole ratio between them now. Now write mole ratio between the two reactants. Here we have 2 moles of Al to 1 mole of Fe2O3. Now select any one of them. Any one of them will give you the same conclusion. If you select Al, then you have to substitute 4.59 in the left side. If you select Fe2O3 in the ratio, then you should substitute 3.76 in the right side. Any one of them will give you the same conclusion. Because this is the first question about limiting reactant, I will solve it in 2 ways, in 2 methods. But in the exam, you have or you can select any one of them. So let's start with aluminum. If you want to substitute aluminum, then moles of aluminum is 4.59 mole. It will be here in the left side, and here is X. In all limiting reactant problems, when you write X, directly in brackets write reacted. These are the reacted moles of iron 3 oxide. By cross multiplication, X equals 4.59 times 1 over 2. Then this will be what? It will be about 2.3, تقريبا 2.3 moles. X is 2.3 mole of what? X under Fe2O3. So this is of Fe2O3. Will what? Will react in brackets. This is react. Why? Compare the reacted moles of Fe2O3 with the exist moles of Fe2O3. The moles that you have from Fe2O3. It's 3.76. 3.76 is exist. موجود. 3.76. Which has a greater value, the reacted moles or the exist moles? Yes, the exist moles is greater than 3.76. This is the exist moles is greater than 2.3 mole, which is the reacted moles. What does it mean? It means that the exist moles of Fe2O3 will not react completely. Will not react completely. So Fe2O3 is the excess reactant because the limiting reactant is the reactant that reacted completely. So as Fe2O3 is the excess, then Al will be the limiting reactant. Al is the limiting reactant. This is the final conclusion. As I said, because this is the first problem, I will solve it in two different ways. If another student selects in this ratio here, if he select, let's say if he want to substitute the moles of Fe2O3, so what shall he do? He will do like this. Again, 2 mole of Al to 1 mole of Fe2O3. This time we will substitute the moles of Fe2O3, which is 3.76 in the right side. 3.76 mole here, and X will be here. These are the reacted moles of aluminum. So X by cross multiplication is 3.76 times 2. 3.76 times 2, this is 7.52. So 7.52 mole of Al will react. Now compare it with the exist moles of Al. We have only 4.59 mole. While 4.59 mole exist. Here, the reacted moles, 7.52, is greater than the exist moles, 4.52. This is the exist. Here is the reacted. So what does it mean? It means that the entire amount of Al will react. So the conclusion is that Al is the limiting reactant. As you can see, we ended with the same conclusion. So regardless which material you will select in your solution, you will end with the correct conclusion and the same conclusion. Did we solve the problem? Not yet. Now, this procedure is applied or was applied just to determine the limiting reactant, just to distinguish or to identify which one of them is the limiting reactant, which one of them is beef, and which one of them is bread. Here, the conclusion, aluminum is the limiting reactant. The question asked me to determine what? To determine the mass of aluminum. How many grams here? Calculate the mass of aluminum formed. So because sorry, the mass of Al2O3 formed. Because aluminum is the limiting reactant, then here now I have to write the ratio between aluminum and the limiting reactant and the product. I cannot select iron 3 oxide because iron 3 oxide doesn't limit the amount of product, it's the excess. The ratio between them is 2 to 1. 2 mole of Al, which is our limiting reactant, to 1 mole of Al2O3. How many moles of Al do we have? We have 4.59 moles according to the first step. And here is X by cross multiplication. X تقريبا it's approximately 2.3 moles of Al2O3. We did not solve the question yet because the last step is to convert moles to mass. 2.3 mole equals mass of Al2O3 over molar mass. The molar mass of Al2O3 is let's determine it. I think it's 102. 2 grams. So the mass equals the final answer is 234.6 grams. This is how to determine the molar mass. The last topic in the chapter is the percent yield. The percent yield. What do we mean by percent yield? Percent yield equals the actual yield over theoretical yield times 100%. What we mean by actual yield and what we mean by the theoretical yield. Let's say you have a reaction between A plus B to produce C. You did your calculations and you applied the stoichiometric principles and you concluded that by calculations you should end with, let's say, 100 grams of C. 100 grams of C. Now this amount, 100 grams, this is just a theoretical amount. Theoretical amount. Or it's called theoretical yield. Now if you decide to carry out the reaction by yourself and to carry out the experiment between A and B to produce C and to check by yourself whether you will end with 100 grams of C or not, then you should apply everything by yourself experimentally, practically. Let's say you apply this reaction in the lab. You reacted it with A with B by applying the suitable circumstances, and you ended with C. But when you weighed C, when you got the mass of C, you found that the mass of C is, let's say, 70 grams. Now, if I ask you, what's the efficiency of your work? What the accuracy of your work? What you will say? Yes, you will say it's 70%. Why 70%? Because you expected to end with 100 grams, but actually you ended with 70 grams. So the efficiency of your work is 70%, which is 70. The 70, this is the actual yield, the actual amount, the practical amount, or the experimental amount, over 100, the theoretical amount times 100%. This is how to determine the percent yield. It's here. The actual yield is the experimental amount of the product. It's 70 in that example. Over theoretical yield, it's the calculated amount of the product, which was 100 grams in the previous example, times 100%. Example. 3.75 grams of zinc reacted with excess hydrochloric acid. So hydrochloric acid in this equation is excess, which means zinc is limiting reactant. Directly, we concluded the limiting reactant. وَكَفَى اللَّهُ الْمُؤْمِنِينَ الْقِتَالَ. Because the question gave me the excess reactant directly. 3.75 grams of zinc, here it's given 3.75 grams, reacted with excess hydrochloric acid. 5.5 grams of zinc chloride were collected. What did you conclude from this statement? Were collected. Is it calculated or experimental? When we say collected means you collected them by your hands. Yes, this is the experimental yield or the actual yield. So the actual yield is given. What's the percent yield of this reaction? Now apply the law. Percent yield equals the actual yield of zinc chloride over the calculated or the theoretical yield of zinc chloride times 100%, which equals the actual yield is given. It's 5.58 grams over X times 100%. So to solve this equation, we need to determine the theoretical yield of zinc chloride, the calculated yield. How? Yes, by applying the stoichiometry. Stoichiometry, by stoichiometry, we can given any wanted amount by writing the ratio with a given amount. Here, the given material is zinc, which is the limiting reactant, and the wanted material is zinc chloride. The ratio between them is what? The ratio between them is 1 to 1. Here is 1. Here is 1. And the coefficient of zinc chloride is 1. Let's write the equation again here. Zinc chloride, zinc plus 2 FCl, Z and Cl2 and H2. Here is the limiting reactant, which is given 3.75. It's given. And now we need to determine the mass of zinc chloride. So the ratio between given and wanted is 1 to 1. Write it here. 1 mole of zinc to 1 mole of zinc chloride. We don't have moles of zinc, we have mass of zinc. So here we should convert mass to moles. Mass of zinc to moles of zinc over molar mass 65.38, and here is X. By cross multiplication, X equals 0.5 0.057 mole of zinc chloride. This is the theoretical yield. Theoretical yield. But be careful. Here, percent yield equal the actual yield over theoretical yield. Here, the actual yield was in grams. And now we got X in moles. Can we divide grams over moles? No, we cannot. This is why you should convert moles to mass. So 0.057 mole equals mass over molar mass. What's the molar mass of zinc chloride? The molar mass of zinc chloride is 136.3. So the mass is 7.8 grams. 7.8 grams. This is the theoretical yield. Now we can easily substitute it here. The percent yield equals the actual yield 5.58 grams over the theoretical yield that we just determined, which is 7.8 grams. 7.8 grams times 100%. The answer is 71.5%. This is how to determine the percent yield of chemical reactions. Here you can solve this problem at home. Same procedure, same everything, same idea. You have a reaction between P4 and 6F2 to produce PF3 according to this equation. What mass of P4 needed to produce 58 grams of PF3 if the reaction has a 64.9% yield? The answer is given. Try to solve it by yourself. Thank you very much. Assalamu alaikum.